I will start recording. Welcome everybody. Thanks for your attendance, and we're going to have our keynote speaker for today. And well, I usually don't use virtual backgrounds. However, I thought today I should use this as we celebrate the GIS Day. And I would like to see a quick show of hands. Who knows anything about this map? Just one? Maybe I can do this. No, not a clue. Okay. Well, it's a map by Peter Reis, who was an admiral and cartographer in Ottoman, and it was one of the most accurate world map in the 16th century. Well, we're all interested in maps and love to learn more about them, right? But this has another special attribute that tied today's speaker and me as the host. Both Arzu and I are from the same geography, but surprisingly, two Turkish origin carto lovers, we haven't met in Turkey, not in Europe where Arzu lives, but in the United States. And I first met with Arzu during the GIS Day events in 2018 here in Boston. She had talks at MIT, Harvard, and Northeastern University. And I was fascinated with her expertise in her research area. And once we were having the decision about our keynote speaker, I immediately thought of her. And now it's an honor and privilege to have her as the event's keynote speaker today. She is a professor of human-computer interaction and extended reality at the Institute of Interactive Technologies, University of Applied Science and Art in Northwestern Switzerland. And she's also affiliated with Harvard's Seamless Astronomy team and working on research projects here in the United States. She has tremendous research effort on technology, design, and human factors perspectives on visualization and visual spatial cognition. I think with the increasing complexity in spatial data and the visual complexity of our maps, map-like displays become more and more important. So in the next 60 minutes, we will learn more about the science part of our favorite acronym GIS. So let's welcome our keynote speaker, Dr. Arzu Çöltekin.
Thank you very much, Seda, and thank you for the warm welcome. I'm very glad to see all of you here, even though we are not in person. On the one hand, it's an enabling moment. It's on the other hand, it's bothersome that we can't have natural interaction. So it is what it is. We will move on. Before I start sharing my screen and start showing my slides, I wanted to add something to that map behind you, Seda. It is one of the first maps that shows the Americas ever, and it's kind of a puzzle in cartographic history why and how he might have drawn American coast before America was discovered. So there's like a whole conversation around this, and he himself, the map maker, never left Mediterranean. So apparently he did this map based on some stories he collected from others, like the Portuguese discoverers and such. By coincidence, I didn't know that you were going to show that map. My chapter slide has a historical map. It's not the same map, but it's a historical map. Let's start with the chapter slide. I think I need to switch this so you can see the full screen. So this is the historical map. I just put that one in because I like this map monsters. A lot of the older, well, you guys are here, so I'm looking, that's maybe a better place to look. So this one appears here, and I felt like it's like an expression of geospatial information and one of the ways to collect information and document information about the world that we live in. And Peter Reis map also has some map monsters. So this is just like a symbolic thing. It doesn't really have much more to do with my talk. It's just very nice to look at old maps. Right, so I'm going to start right with a sort of an overview of my research agenda. So as Seda already quite nicely expressed, I'm very interested in human-computer interaction research and extended reality. That is my current position, but I've been properly trained in geographic information science. Actually, that's what my background is. And I took an interest in vision to visualization. My PhD is in photogrammetry, and my minor at the time was cartography. So photogrammetry deals with images and three-dimensional modeling from images. So it's on this end of realistic representations, and cartography is on the other end of the spectrum because it tries to abstract information. So I had a lot of interest in visualization side of things. And this interest continued with a bunch of projects that was started at the University of Zurich, where I worked for like 12 years or so. And many of them, if you are familiar with Bertalan's visual variables, it's almost like a list of that, right? So you like effect of shadow, effect of color, effects of realism, texture. Here it kind of changes a little bit because this is like direct measurements of visual complexity, or how do we design interfaces. There, for example, position also becomes a thing, three-dimensional information, or some gaze contingent paradigms, where I will show you a little bit what that means when we know where somebody's looking. If we have eye movement devices, eye tracking devices at our possession, what can we do with them? So these projects are still kind of active. There's a lot going on about these that are not all like abandoned or anything, but it's where I started at the University of Zurich. This one, the realism one, has a little bit of virtual reality in it. I'll show this example. I'll show some examples from shadow and color as well. I think also like 1 or 2 slides on this one, but I don't have the others because 1 hour is not enough to talk about all of them. Each of these things, this is a hand-drawn graphic. Each of these little things are actual publications that came out from these projects. So there's plenty to talk about. So since I moved to NW, which is another school nearby, it's half an hour train ride, 25 minutes train ride from Zurich. Because the position was advertised as HCI and XR professor, I started doing more XR meaning extended reality, as in virtual reality, augmented reality, and mixed reality. And so I'm writing more of these like papers that are about the state of the art in this domain, and then extended reality research agenda. And some of my newly acquired projects are all in that domain. There's some links between them. It's not completely off. It's still like strongly visuospatial and strongly about knowing about visuospatial cognition. I'm not going to tell you more, just wanted to show you that I've been for a long time in the field, and I have plenty, like a relatively wide range of visualization related projects. And of course, when you see this many publications here, I'm not doing this alone. So this is like a whole bunch of people who contributed also, like in this presentation, you'll see, I always put the names and pictures of people. I feature some of their work. So some of them have worked with me or are still working with me as collaborators at the postdoctoral level. Some of them have been PhD students. She freshly graduated. The defense was only a few weeks ago, and 1st of December, we can call her Dr. Locke. We will look at Ismini's work. And these 3 fellows, I am co-advising different schools. They are active. So recently, because we had new projects acquired, new people joined, we don't have results from those works yet. Just ask me again in 2 years, and then I'm going to show you some other stuff. So now the title of the presentation might be over-promising. So I'm going to discuss about the science of GI science just a tiny bit, and then I will go on and show you some of my work. Now, because the science of GI science is sort of a big word, big sentence. It contains a lot in it to unpack. It would have been a talk by itself. How do we define science? What is valid way of knowing? There are ways of knowing. It's a very philosophical topic. But this was triggered by a recent tweet by this fellow, Sean. I'm pretty sure he didn't imagine that he was going to make it to a talk, his tweet. But he said data science is not actually a science. And then I was like, okay, actually he might have a point. This is like not like this classical sense that is not science. And then I of course, after 2,000 reactions, he's like, I'm not debating it. It was like a tongue-in-cheek remark. And then I wondered if data science is really science. I also teach data science. I think you can do science in data science, but as it is with the current models, current understanding or current culture, maybe it does actually refer to a set of techniques rather than sort of an approach to science. And then, because in GIS, we have this distinction of geographic information systems versus geographic information science, I thought if data science is questionable as a science, can we really talk about an information science, and how would one go about doing information science? Yeah, so there's something called the scientific method. It's probably provocative if you do qualitative research or if you do historical research, but it is empiricist. In essence, it says it's based on empirical observations. It's usually hypothesis driven. It's usually based on controlled experiments. It should be replicable, but it's been a debated area. But it fits to more or less what I do. So I'll just go with that for now and hope that at the end we can debate it together. So with this information science thing, the way that I do information science is that I try to understand how humans process visual spatial information. So visual information and spatial information, they are actually processed in two different parts of the brain, but they usually interact with each other. Everything visual is more or less spatial, but everything spatial do not have to be visual. So by that I mean, if you lost your sight, if you were a vision impaired person, you would still have spatial activity in your brain, because you can collect spatial information also via other senses, by touch, by hearing, by smell. You have all kinds of other means of spatial information coming in. But almost everything that is visual is also spatial. I think that one can say. So I try to understand how humans process that, and I try to translate that into visualization. So if I understand that humans cannot process too much information, then I try to reduce the information, try to understand the limits of that. You will see examples of that. Or if the attention is so that it fails because it leads to an illusion, something is not right, then I try to see if I can translate that information into a visualization paradigm or such. And then I tend to do this vision to visualization thing into randomized controlled experiments. Most often it's a lab experiment. Sometimes we also try to do online experiments. Well, given the COVID and all, lab experiments became harder. Usually the visuospatial stimuli is the treatment. So it's like medicine. You would have medical intervention, and you would have a placebo, and that would be the treatment in that language. And in our case, we say, okay, here's a map and here's a satellite image, do the same thing, and we try to see if one or the other is superior or why. If you take the same map and if you show it in another way, if you take the one map and change the line thickness in the other one, or change the colors in another one, if you have a design intervention, you can say, okay, here's you guys do the same task with this one, the other group does it with that one, and then you have a baseline and you have a measurement, often like that. And sometimes it's the same people doing the same task but using two different devices. And because I'm so interested in vision part, I use eye movement analysis a lot, which sometimes also ends up contributing to visual literature, because in the process, we also, like when you try to learn how humans process visual information to feed to visualization design, you inadvertently also contribute to understanding vision better, because in the experiments, eventually it actually sometimes feeds back that way. So you might find that some of my publications are in learning and memory, biology of learning and memory and stuff like this. So sometimes we have this kind of like interdisciplinary interactions. So all of that, I found it helpful. I did this for myself at some point, and then I put it in a small abstract in a workshop in ICA. How I think about it is that every time you think about producing a visualization or trying to understand if a visualization is too complex or too, if it's the correct amount of complex, because there's a U-curve I'm going to show, there's actually three key dimensions. And one is that's the technology and design factors. And the other dimension is human factors. So who are you preparing this for. And here, obviously, the decisions that you make about technology and design. And then there's contextual and task-related factors. These three basically encapsulate every variable that there may be that matters about your decisions on how to prepare visualization. Here you have cognitive and perceptual things going on. This is actually a continuum. Sometimes perception is influenced by cognition and vice versa. So they are not like a binary exclusive things. It's also the neural system is like this, but there is still some sort of distinction. Perception is a little bit more pre-attentive and cognition is more about what you already know. So things like visual abilities, like if you have a clear age-related visual ability thing, that would be a perceptual problem. If your lens gets a little bit yellower, you can't distinguish blue shades as much, that's a perceptual question. Or other things like peripheral vision, etc. And the cognitive stuff could be about your visuospatial abilities as measured by standardized tests. It could be like how good and how fast you are in conducting spatial tasks. It could be about expertise. All of you here, even if you studied 1 year of geospatial stuff, you are actually gonna do better than an average person in some of the spatial tasks. So that kind of stuff with cognitive culture education. And among the technology and design factors, we can talk about display types. That could be something like, is it a satellite image or is it the map? Could be elements of design, line thickness or color, or it could be the HCI part with the interaction. Am I doing it this? Am I interacting with the visualization that way or that way? You can also put computational performance here. You can do science of computational performance if this is necessary. In geography, with remote sensing data and virtual reality kind of stuff, you also have to sometimes worry about level of detail management and stuff like this. So I already said the examples. I'm gonna leave that so that I don't use the entire hour on this graph. And the contextual and task-related factors could be, maybe you can think of them as high level and low level. At the low level, it's more about the cognitive processing. At the high level, what your goal really is. For example, here, you could say that every time you read a map, you probably try to locate the information, you try to identify what it is, maybe compare it with something else, maybe associate it with what you already know, maybe try to remember and eventually learn. Short-term remembering versus a little bit long-term retention. These are all cognitive processes. In the high level, you can say that, okay, context is that I'm now doing it for wayfinding. I'm driving an ambulance, right? That's going to change everything. So there, if you're driving an ambulance, speed matters. You have to measure speed. Your visualization has to facilitate. It should not be, there should not be like learning curve. If you need to put audio as a support or whatever. If it's about scene understanding or diagnostics or planning for touristic plans for next summer, then you can say, okay, speed is not the key thing here. It's more the richness of information or alternatives. So all of these things together interact with each other, and you have to basically choose how to combine them together to create the most functioning, best visualization. Let's look at cognitive example. Why would cognition would matter? Here it's this information processing approach, and I like this quote: "A wealth of information creates a poverty of attention." So what happens is that if you show too much of something, it can actually be bad. I think cartographers know that for ages, because generalization is built on that. So if you look at other domains, you will also see that. For example, this was a management-related paper. I think it was from something about accounting, marketing, etc. So they have been looking at how decision performance is affected by the amount of information. So let's say you are shopping something, you have 5 options to compare I don't know which detergent to buy. That's okay. When you have 25 options, it gets too much. So what is the sweet spot? It's like too little is, you have no information. You have only one option that might lead to bad decisions, and too much similarly is actually detrimental to good decisions. So this is true for all kinds of things. And where is that sweet spot? It relies on this Miller paper from 1956. If you haven't heard of this paper before, I think you should know about it. It's kind of a classic. And if you have used Color Brewer ever, that has the 7 categories as a default. And that 7 categories is actually informed by this. So cartographers say, don't do more than 7 classes if you can avoid it in a thematic map. And this is coming from there. It's the magical number 7 plus minus 2. Now, this magical number 7 apparently appeared in his dreams and persecuted him. He's a very playful writer. I think these days we couldn't publish it in this exact language, but it was how it was written back then. So it's also fun to read. So go ahead and find that paper if you didn't know about it already. But what he basically says is that working memory capacity sort of saturates around 7. So if you have 7 numbers, you can do it. 7 detergent types, you can do it. 7 road types or colors or whatever, you can do it. But after that, for a lot of people, it's harder. And this is in more modern literature, somebody said it's actually rather 4 plus minus 2 and not even 7. So I think it depends on the crowd. I think we should do a global study to see where the exact sweet spot might be for that. But this plus minus 2, it can be, you can actually catch that with very simple tests like the water level task. This is something I learned from Lynn Libben as an American psychologist from Penn State in a talk, but it's actually from a Swiss scientist. It's a twisted world. For Piaget, it looks at the child development. Now, the question he would ask children is that, here's a bottle. Imagine that this bottle is half full. So this half of it is, let's say, it has water in it. And I tilt the bottle. What happens to the water? Can you draw me where the line would go? So people draw things like this. So this person draws the water line here, and this person draws it so, and this person draws it. This is actually from a study that I conducted myself. I collected data from 2 different schools. I also collected data from geography PhD students, and at some point, computer graphics people, they don't make any mistakes. Huh? But so there's a self-selected bunch who are not going to make that mistake. But in psychology undergrads, apparently up to 30% could make these mistakes. That was Lynn's study. And in the high schools that I studied, in a grammar school, science-heavy grammar school, it was somewhere in the range of 7 to 10%, or in another one, it was very high, the number of mistakes. The answer, of course, I mean, I guess I don't have to tell this crowd, is that it's always supposed to be parallel to the ground because water is liquid. This one is almost like, if you forget that water is liquid, it almost makes sense because somebody takes the bottom of the bottle as a reference, but so you can, if somebody doesn't do well in this task, the chances are they're not going to be very good at map reading, for example, or orientation and things like this. So you can catch these cognitive ability or interpretation of spatial tasks and then translate them to more complex tasks. Here's an example. So it's a Atlas of the US. It was a 2000 version. So the study is a little bit old. But I mean, the studies from 2009 and 10, but the map was from 2000, the data. So we told people, we first showed them where Maine was, and then we told people that they need to catch a crime incident in Maine in 2000. So what they had to do is they had to go and find Maine, and they had to go to the legend and read something and tell us the answer. And what you see here is eye movements. So these little graduated circles, the little circles, they are showing somebody's eye movements. You can see the order, the numbers in the middle are the order. And you can also see the size is scaled to the amount of time they spend looking at this place. So this person spent 11 seconds and about 25 fixations. A fixation is how long you look at something. So you look at something long enough so that you register the information, because if you move, there's a saccadic movement. If you move your eyes really fast, you can't actually register the information. It's usually like a blank experience. It's a very nice video for that, but I don't have to next time when we do a lecture. So this person takes 11 seconds and looks at 25 places and gets the right answer. Now, be prepared for the next person doing the same task. So this is the person who's also looking at Maine. You can see that the person is already like zooming into the the west coast to begin with. So they are already lost in the map, even though they have been told where Maine was in the beginning. And they take 521 seconds compared to 11 seconds, it's an insane amount of time. And after 1,181 fixations, they probably give up and I don't remember if they were able to give the answer. Now, of course, it doesn't mean that this person is stupid or anything. I mean, no judgment there. It may be that they didn't sleep the night before. It may be that they are on some sort of medication. It may be that there's some anxiety that kicked in because somebody was watching them. But I use these slides usually to tell my students that, you know, this could be you and this could be your client. If you are preparing maps, don't test it just on yourself and your classmates, because you're going to do great and you think that everything is working and it may not be true for the others. So another example from cognition is about age. So that was not about age, that was just two people in the same age cohort, more or less. But we can also look at aging, and we have done a huge project about aging. I have another one currently on my table because it's a, you know, I'm kind of worried when I'm 70 years old, we are going to be 30% of the population, and I think we will never retire. So, so we need to stay functional. Huh? So, so we are looking at these projections. I think there was also this from this side. There's also the 2100 projection. If you look at aging, it's a depressive graphic, but from 20s, so this is your age, your 20s, 30s, it goes up to 80s. And this is like short-term memory, working memory, long-term memory, speed of processing. So everything is going down. And it's going down pretty linearly. And this kind of is like, you know, senior moments are real. You don't process as much, you don't remember as much. Okay, so there's one good news. So that's experience-based verbal knowledge. So that kind of stays the same, and in fact goes up a little bit over the course of life, which means that you still have to respect your supervisor. I think as real as senior moments are, wisdom is also real. So it's not like we should discard older people. It is some. So I'm already kind of in the flipping to the other side. So I have to also protect the honor of the old people. Right, so we looked at a study where we compared older and younger people. So this was a virtual environment study where we explored this information load idea, and we wanted to see if this is the same for older and younger people. So Ismini did this, she was the lead. We have a number of publications other than this one, but I'm going to feature that one a little bit. So we manipulated levels of realism because we thought that too much realism could be too much information. And we changed the position of the landmarks and we gave them a navigational task. We said, okay, learn your route. This is quite meaningful in an aging study because one of the first things that seems to give in is spatial memory. So like one of the earliest signs of malfunctioning memory is spatial confusion. So visual memory, verbal memory is spared a bit more. So this is like an interesting side effect of that navigation is very important for independence. So we looked at route learning abilities. So we did an age group and a spatial ability group. So this is our experimental design. In statistics, this is called the factorial design. Again, we use these 3 dimensions, similarly as what I introduced. So we have participants here, a group of 20 to 30 years old people, about 42 of them. And then we have another group that is 65 to 75. We gave them 3 kinds of visualizations. I'll give you the examples in a minute. And we gave them 3 kinds of tasks. We gave them tasks that were predominantly visual, meaning that you needed the photographic information to solve the task. And visual spatial would be both photographic and non-photographic, and spatial would be really just very purely about orientation, like have you turned left and right, or were you facing north in the beginning and in the end after you took several turns. So it would matter for the findings later. And then we counterbalance this study for gender and expertise because that can affect something. And we repeated the memory questions 1 week later. And then we measured their recall accuracy and we measured their confidence. We also looked at task time and eye movements, but this analysis is still ongoing. And then we randomized the order. This is the controlled, randomized controlled lab study. You're supposed to do that too, so that, you know, if there's any learning effect, it gets distributed. So this is how the stimulus looked like. It was like the story was that you were sitting on a passenger seat. somebody was taking you somewhere, somebody's driving you from A to B, and you're going to do this again on your own later, so you should pay attention. So we have given them very sort of explicit learning tasks, because incidental learning here wouldn't be easy to manage. So this is how the realistic one looked. We hypothesized that this may be too much information to remember all the details. Sometimes we would show them a screenshot and say, did you see this? Did you not see this? As a baseline, we gave them also this like completely non-textured, like shades and everything. Everything looks the same, to be honest. I thought they were gonna tank here and nobody would remember anything, but they surprised me. And then we designed this one where we put the textures only at the intersection points and in the direction of turn. This is something the navigation literature says is important. So we apparently pay attention to these features. So we highlighted them, so it's even more pronounced. And then we left the roads also textured, because it's supposed to help a little bit with structural saliency, so that you might be able to, I guess, remember a little bit the linear structures. So this is how the results look like. I know it's a lot to unpack here, but I'll help you and you'll be fine in a minute. So we have the younger participants on this column, and we have the older participants here. So this is their recall accuracy performance in the top part in visuospatial tasks. And in the bottom part, we have 1 week later, the same questions they answered again without having seen the video again. So what is interesting is, you don't have to like read everything here, but what is interesting is this U curve. You can see that this green part refers to the mixed one, where we use the texture selectively, and it wins every time, right? So it wins in the younger group and the older group. It wins again in the 1 week later and for both groups too. And the loss of information from week 1 to week 2 is actually not statistically significant for this condition. So if you have been learning with this mixed realism condition, you forget about 8% of what you have seen. And if you have been learning with the abstract, you lost 20% of what you have seen. So this you were remembering 66% now and 44% later. So this is how it looks. And you can see also, of course, clear age differences here, but we are focusing more on visualization to see if it helps whether you're old or young. But there's also all kinds of individual variations. So there are old people who are doing better than young people among the cohorts. So we're looking at averages now. So you have to remember that. All right, so this is how it looks. Which is very interesting is also that it kind of helps with calibrating people's confidence. So we asked them how confident they felt about what they remembered. It is a known phenomenon in the literature that older people also tend to be overconfident about memories. I think that it's maybe, from my interpretation, I think that it's maybe to do with not being able to tell apart. Like if I was in a classroom and you put me in another classroom that was more or less the same, I might feel that, okay, I have been here because I don't have a lot of details. Maybe it just looks broadly similar. So I feel confident that I was there. So this is something that, like, again, the same type of organization. You can see that when the confidence levels are close to the center, that is close to their actual performance. And you see the older people are actually overconfident and the younger people are slightly underconfident. And then if you go 1 week later, the confidence actually grows for all conditions with the older people. They feel even more confident about what they remember and what they cannot remember. For younger people, there's a curious thing here. Their performance was best with this condition, but they don't feel it. They feel that this is not the best. They feel a bit less confident about this one, which we can't quite explain. I think we need to study this a little bit more, but we kind of interpreted that underconfidence is not as bad as overconfidence. So if you're like, okay, I'm done, I've learned what I need to learn, I'm gonna go out and drive, and you didn't actually learn, that's bad. If you're underconfident, you might just, maybe repeat the task a few times until you learn. So this is not so bad, we think. Of course, it might be loss of time. In some cases, you can argue that it's not still ideal, but it was, if you have ideas, I'm happy to hear why this may be the case. So what else is interesting is we also asked them if they prefer. So there's this concept called naive realism. in cartography as well as in other domains. These guys are psychologists, but it has been also translated as naive cartography to our domain. So people prefer realism as a display principle. They kind of like it. We like it. We like photography. We like 3D and interactive things and animations. But it's not necessarily always good. You know, it's called metacognition. So you might like it even if it's not good for you. So we asked them too. So we showed them this 3 and we said, you know, you were going to learn around which one you would go with. So before the experiment, 88% of the younger people said, yeah, we like the realistic one. And 97% of the older people say they like the realistic one. 3% picked the mixed here and 12% picked the mixed here, and nobody wanted the abstract, which is not surprising. And after the experiment, a lot of the younger people shifted their preference. Now 70% prefers the mixed, which basically is interpreted as metacognition. They understand that this helps them more, and now they prefer that. But I mean, in the old people, you have less of that, the same phenomenon, but not everybody does that. So majority is still staying with their original preference. I think that maybe confidence is a more interesting measure for naivete than preference, because preference is tricky. I mean, sometimes we buy things that we like for, like, it may not be functional, but we like it for other reasons. I mean, sometimes you buy high heel shoes and, you know, that's not like, there's no argument from the function that that's the good choice. Or you might buy an outfit because it just, you know, you like to touch it, but it's not the best temperature regulated textile, whatever. So it's possible that you understand that what is better, but you like it for different reasons. So preference, I think, is a bit tricky, but that's what the original authors used. So we try to replicate this. So it's interesting in some way. So this combination of like the sweet spot, it's not only about performance, but also about confidence and preference. So I still have I still have like good 20 minutes. So I'm going to give you a couple of more examples. So this was a cognition motivated study. And here's a couple of perception motivated studies. One thing that I've done a little bit earlier with including my PhD was something called foveation or gaze contingency. So your eye has a little spot called fovea on the retina, which manages the level of detail in the world for you. So when you look at the world, you don't see it in a uniform resolution. So on the sides, for example, if you look at the center, things on the periphery are not going to be sharp. So when you're reading, something like 4 to 5 letters are going to be in focus, and then actually the rest is not in focus. So the world isn't processed in a uniform way by your visual processing system. So this knowledge becomes useful if you have an eye tracking device and you know where somebody's looking, right? So for example, cameras do that. Like if this is a picture I took in Amsterdam, I never asked their permission. These kids might be adults now. I hope it's not one of, like if it's one of you, tell me, I don't know. But you can do that, like shift of focus, right? So if the focus is here and here and here, you can show the rest of the scene blurry. And if your eyes were following this blur might go completely unnoticed, because this is what your eyes do anyway, right? So if we know where somebody's looking, and eye tracking can capture that gaze point and render the scene accordingly. So this is what we have done. In fact, I did it for 3D. That was a big part of my PhD with the stereoscopic visualizations. So you can actually discard something like 72% of the image if somebody's looking at the corner, and they will, ideally, it will go unnoticed. So you can, depending on where the point of interest is, you can discard a lot of information. You don't have to render it, or you don't have to stream it if you know where somebody's looking. So that was one of the key arguments. And then after I moved to Switzerland, we got a SNF project from this. So you could do a blur on the edges, or also depth of field. If it's 3D, you could do color. Color is also not so well perceived in the sites. And then you can combine them into the thing. And then we asked people, we asked people some search questions or so, and then we looked at their task completion times. So it looks like the foveated or gaze contingent display was slightly faster than the uniform display, which is interesting because I originally didn't expect this, but then I think that the interpretation might be that you reduce overall entropy. So you are showing the images a little bit blurred on the side, and your eye still discards more information from that. But incoming information is already at a lower level. So maybe you have some bandwidth to use. So it's a subtle effect, but it's quite stable. Right, so and then we asked whether they notice any visual artifacts. I mean, if this is happening in real time, if you're looking at the center, you're not supposed to see this effect, right? So this is what we tried to capture, and it looked like, you know, they were noticing something, but in all three conditions, meaning that they were noticing something for the non-uniform image. So that was another PhD project. And then I did some color thing. That was Alžbeta's project. This is an illusion. This is not what she did, but it's a fascinating, famous illusion. I think many of you know. A and B are the same color. And this is now again a trick from the shadow. Yeah, so I think it's it's almost like an internet meme. Okay, so what Alžbeta did, however, was that she wanted to understand what is if can we quantify the discriminability of the two shades of the same color. So if you have, for example, A here and B here, and ask people, are they the same or different? So you would ask them over and over again, you would manipulate the position of these things, so you would manipulate the surrounding colors. If this is surrounded by darker colors or lighter colors, it may be perceived slightly differently. So these two are, I think, like one delta E different. So if the delta E, this is a perceptually driven measure of color distance. If the delta E is 20, it looks like this. It's clearly distinguishable. If the delta E is 2, it looks like this. And this, if you you really pay attention, you can maybe see it, but it's hard to distinguish this. And if you separate these from one another, so if they are not really next to each other, it becomes impossible. And surrounding colors are also important. So we have been establishing a number of studies with different colors, a lot of online studies, offline studies. So around delta E10, the effect seems stable, that everybody can tell the colors apart. So this is like a practical cartography lesson that we took from this study. And they have, Alžbeta and one of her friends, they actually wrote a web-based tool to come up with this delta E as a measure. I know that internet is full of color tools, but here is one more that comes from a PhD project. So you can explore that if you like. In a recent study, this came fresh out, actually just November, 2 weeks ago. It's about rainbow colors. Has anyone in the room not heard that rainbow is bad? So it's something that the internet keeps saying, rainbow is bad. There's an internet police that will say rainbow is bad. Anyway, so we looked at the rainbow, and if you look at the literature from 60s, the red here means that the study, if they are user studies, the study shows that the rainbow didn't facilitate. So if you use rainbow color scheme, people failed in the tasks. They were either slower or they were making more errors. But if it's green, it's okay. They were doing fine. So if you look at the pattern or outlier detection, rainbow was hard. People were not doing well. If you see a lot of red here, with some exception here. And then you have reading details. If you have a thematic map, if you need to match a red in the middle of the thematic map to a legend, it was fine. And then for ordering or having some boundary detection, then rainbow was bad again. Here, dominant, it's really, really red. So what we did was we took sort of 11 different tasks that included ordering and other tasks, and 2 map types. And then we have been, this was Isa's study, and she invited me to this paper after actually she did the study. So my contribution is limited, I must acknowledge, but it was writing the paper, we did it together. So she collected data from 544 high school students, so it's a relatively large study. So first thing was to ask them to order quite explicitly these colors into some sort of order of if the value that they represent is large or small, so order for magnitude. And you can see that this is the outcome from the rainbow colors. So a lot of people here, the 96 people, this is the count, ordered it like this, which is obeying the rainbows in the nature. They must have seen it in their physics classes, but there's so many variations, a lot of individual ordering. There's no clear order when it comes to this one. But if you take this one, dark to sort of dark is more, kind of comes out. If you look at the sequential color scheme for the same value, however, it's a huge agreement. I mean, there's 216 times people actually order it like this. So dark is more and light is less. And here only 18 order the other way around, and the others couple of unique values. So ordering is hard with Rainbow. People don't really agree with it. We also gave them extra tasks that are to do with ordering, like indicate maximum value, which would require you to compare a couple of values, or indicate minimum, or compare units. And here again, in all ordering tasks, even if they are implicit, Rainbow didn't facilitate well. Sequential colors were absolutely better. And despite these ordering effects, I mean, in the other tasks, by the way, the results are mixed. So like reading details were fine. Recall wasn't so bad, but so it's like if you're going to use Rainbow, you have to understand for what you're using it. But this is also interesting. So we took like a bunch of publications from remote sensing and planetary science, not planet science, planetary science journals. And we looked at if the Rainbow is commonly used. So of the 355 papers we analyzed, there's about 46 to 70%, depending on the journal, that actually uses Rainbow, even in the color. So it's like an extremely common, extremely popular thing, probably because it's software default, or maybe because it's just lovely. I mean, we love rainbows. I mean, we love them for many reasons. I don't know, like nature has this beautiful rainbows, and I don't know. So shadow. Now I'm moving from color to another visual variable. And this is a meme as well. So many of you might have seen it. So this could be a pie chart until you have seen the legend. And once you read that as sky and the sunny side of the pyramid and the shady side of the pyramid, you can't unsee the 3D shape. It just becomes this three-dimensional thing, and it just, I can't see it in 2D anymore. This is to say that shadows are important for three-dimensional perception. Another interesting thing is about hollow face masks. So this is about 3D perception as well. So what's happening here is that you are rotating this mask, and at some point you're looking at the mask from behind, right? So this is the front, and now you're looking at the mask from behind. And when you look at the mask from behind, your mind is like, yeah, okay, I have seen noses a million times. Let me correct this for you. I mean, it's kind of like a competition between cognitive knowledge, silent learning, your mind as a statistical machine, interfering with your perception. So your perceptual signal, if you were interpreting them from raw, you would see the nose going concave, which is like not working in these conditions. Your mind is like, no, the noses, I know how they are. So let me just retrieve it from the previous knowledge instead of like making you all over fresh interpretation. This leads to a lot of interesting conclusions for other cognitive biases, which I also gave a talk that's to do with gender and ethnicity and race and all that. Like, you know, how your mind makes these categories and maybe recalls those, and you're not aware of it. You're like, can't help it in some way. I guess that you need to work on that very strongly, not to like be unfair to people. Right, so this also happens with cartography and maps, and this is a satellite image. This is Grand Canyon, Colorado River, and if you see it like I do, it looks like the river is flowing on a ridge. And if you rotate it 180 degrees, then it looks correct. The spatial relationships are restored. This happens because the shadows are on the southern slope, and we use the maps north up. And if the shadow is below, your mind is like, yeah, I know where shadows normally go. This should go below. Everything is in order. The light is above, shadow is below. If the shadow is on the other side than you are expecting, so the northern slopes are actually in shade, then it reverts the image for you. So this is what happens. It also happens with terrain. This is called light from above prior or assumption in psychology. It's relatively well documented. So here you can see a chocolate bar. When you rotate, it becomes a waffle. So that kind of thing. So this happens all the time. It's very common. So we looked at the prevalence of this. So with the Northern Hemisphere images, if you show people this kind of images and ask if A is higher or B is higher, or if you ask them whether it's a valley or a ridge, about 40% of the time they can tell, about 60% of the time they can't tell. If you rotate the image like you do here, then the success rates go double. And if you take the Southern Hemisphere images, it goes the opposite. So you can rotate them, and all of a sudden you break the spatial relationships or the 3D perception. So we took like here with the satellite images, it's hard to control. So we took a terrain and we played with the light source and we played it all around the clock. And then we looked if people can tell if this is a valley or a ridge. So we would ask them, is this clearly a valley or clearly a ridge or something in between? And this was Julien, a master's grad student. 2 publications from the master's study, very successfully done. So what we did was to illuminate the terrains from the 0 degree north and then 22 degrees, 22.5 degrees stepwise all the way around. And you would have multiple terrains, sometimes ridges, R is for ridge, sometimes valleys. And then we changed also, we controlled for the terrain orientation and we created these different terrains. And we asked the same question over and over again. It must have been really boring to be a participant in that study. So this is how it looks. So if you look at the blue, that means that people actually can identify a valley as a valley. And red means they don't. So the southern angles are all red and northern angles are kind of all blue. And in this, somewhere in the range of the middle, you have some more ambiguity or disagreement. Here, like half of the people will think that it's a valley and the other half will think that it's a ridge. So there's some disagreement. So what's interesting is we found this to be at the north-northwest. Cartographic convention is just a little northwest of that. And then the top was also kind of better than the cartographic convention. We are trying to replicate this in multiple different studies. And there's a kind of a left bias, right? So it's not that the light is from above, but it is slightly above left. So this one, we asked, why should it be left? It's a non-bias. We found left bias in 13.4 degrees. The others found it at the 22 degrees or so, but handedness mattered. So if you were left-handed, you had 24 degrees. If you're right-handed, it was 27. If you are left-handed, it was 7 degrees. If you were right-handed, it was 23 degrees, depending on what the studies. And these are not very big studies, so we are collecting more data on this one. And why should it be so is that the theory is that not that the light is coming from above, which is what is assumed, but that if you are right-handed, you are turning yourself perhaps a little bit towards the light that way, so that the light comes from the left for you, so that you avoid shadows with your manual work. Whether you're writing, whether you're doing something else, your hands will be better illuminated if the light comes from left. So you would assume that if you're left-handed, you should have a right bias. But because the left-handed people live in a right-handed world, like when people build schools, apparently they will put the desks so that the window is on the left side. Maybe they learn a little bit or they compensate a little bit. Yeah, this is also kind of an interesting sidetrack. Confidence we discussed about the older people. Another known phenomenon is men are overconfident. And in this study, we also looked at this. So this is the mean accuracy. So you have females and males doing quite the same. Some experience, if you are a bit experienced with maps, it helps just a tiny bit, but not statistically significantly. If you look at the confidence, at first we just looked at men and women. It appeared that men were overconfident and women weren't. But if you split that by experience, the less experience men have, the more confident they seem to be. And the experienced men, they have similar levels of confidence as women, whether they are experienced or not. This is quite interesting to me. It's also kind of shown in literature about these confidence differences. Usually people frame it that women are underconfident, but I think in this case, it's clearly overconfidence on the male side, especially the inexperienced male side, because I mean, this otherwise it's on par. I mean, everybody else is kind of predicting their performance quite well. So that's a kind of a sidetrack finding. I want to do more on this as well to better understand how we socialize boys and what is this coming from and does it mean anything for GIS. Anyway, it's interesting that experience does something. I think that's an important observation too. Oh, sorry for the quality. I think maybe my Zoom is doing something. Doesn't matter. I'll go over this very quickly. We compared this in this very study. We compared terrain with satellite images. So same terrain, black and white, and color satellite images. And you can see that on the terrain, when you show people the terrain, the agreement is pretty high. So here's clearly a valley, clearly a valley, clearly a valley, or whatever was the answer. And if you show the satellite, the distribution is different because you show them vegetation, you show them snow. If there's snow on the valley floor, they might be like, okay, yeah, but snow doesn't really happen in the valley floors, right? So some people probably interpret. So we also compared that. And you can see that the success rates with shaded relief maps, if you show them like this, was somewhere in the range of 2%, but with the images, you have a bit more. And the confidence here, again, is like the stronger the illusion, the higher the confidence. So if you have a strong illusion, people feel confident about their answers, which also is very telling for our other cognitive biases. So we know that it occurs in shaded relief maps and satellite images. We know that it's very prevalent, this terrain reversal phenomenon. And we know that the texture reduces and color kind of strengthens the illusion. And there's a left bias. And there's handedness in the left bias, it might matter. And yeah, I mean, this is kind of the summary of what we have said. And it's kind of fixable. So we also have a recent paper about how this is fixable. More work is coming up. I don't want to say more, but we are looking at like the levels of terrain, ruggedness, and effective expertise, etc. So this project is quite alive. And now my last slide. I think now I'm also wearing you out with your patience. So I wanted to say that, like, you know, working with visualization can be a lot of fun besides, you know, leading to new insights and hypotheses and knowledge. And it has a lot of practical implications too. If you can design the visualization right and well, you can actually help people. You can help people learn, remember, navigate more efficiently. So it's important to understand these factors and how they interact, and do what you can and test it on the target user group if you can. And yeah, current GI science perhaps is a little bit tech driven, but you know, we have to also acknowledge that we need it. We need the tech. We can't really function, or we can't really move forward without technology research. And the science of GIS, geographic information science, is happening too, and I think we equally need that. So the reflection, the testing, the rigor, and the applied science kind of connecting the two, and many of us probably are actually in this area. So trying to understand the science, but also think of the relevance of to people today. So with that, I wanted to pitch that one as a community effort, 10qviz.org, that you can contribute, come for a conversation, send us a blog post. We are starting this with a colleague in Harvard, Alyssa Goodman, an astronomer. So thank you very much. That's it. If you have questions, I'm happy to take them. And I'm not like extremely over time.
Yes, thank you so much, Arzu. I really enjoyed your talk again. And but let's see if I have some questions, but let's see if somebody would like to speak up first. There are some also questions in the chat. Maybe you would like to start from that.
Should I stop sharing the screen? Then I can see more. Yes. The chat is easier to see that way, but if we, for the discussion, if it facilitates, I can share the screen again. So should we look through the chat window, Seda, or would you like to start?
Let's see. The ones who commented maybe, but I remember, I think.
Thank you, Becky. Which visual that you love?
It was visual complex, the framework. I also like that too.
Sorry, it's extremely complex, but I think it covers a lot. So I'm glad that it worked for you.
Yeah, it certainly helped having your explanation of it, but it made a lot of sense. You know, as somebody who never took a cartography class, I kind of realized as I design things, I am thinking about a lot of those things, but I'm not thinking about all of them, and I should. So I appreciated that.
I'm glad to hear that. It's good to kind of like have a sort of a systematic way of organizing it. I think that it helps designing experiments, but also making visualization decisions. It helps me, so I figured it might help others too. Yeah. And Garen said something about the parents. Garen.
Well, so I'm a geography student at Clark University, and my parents, one's a school teacher and one is a businessman. And so they don't know anything about maps. And so I'm usually making a map. For example, one of my professors is in the chat, and I'll be making a map, and I know I'm making it for her, but that doesn't mean it's readable for someone else. And so I usually get my dad on the phone, and he'll say, I don't even, like, what is this even a scale of? I don't even know what you're referencing it to. And so it's very helpful.
Helpful, right? Yeah. Very
That's
good.
a perfect example to the final slide you showed that says number 1 is who are you showing to, you know, like that's.
Yeah, exactly. One of the 10, then the first of the 10 questions. Yeah. Who are you showing it to? I mean, aging has a lot of interesting side effects. It's not only in cognition, but also perceptually. We all experience that to some degree. I mean, there's a lot of individual variability, but some people also lost their hearing function or I mean, visual acuity. I'm starting to feel the reading glasses are coming on to me. So all kinds of things happen when we age. So. And also younger age is interesting because at the developmental age, you also have a different group of abilities. They are not yet fully developed. So yeah. I also use my own parents sometimes for guinea pigs, for guys.
To speak to the developmental component, sometimes I'll give lectures for like my high school that I went to about what geography is, because there's no geographic anything there. And thinking about, you know, I'm in this world of geography, and what would be useful for someone who's never seen it before is very interesting as well.
Yeah, absolutely. Yeah, I find it fascinating too. It's one of the fun things about doing user studies, the surprises. Yeah. Very cool. And Becky has been kind to put the links.
Yeah. So I had asked a question in the chat that other people answered. It was, what is the default angle for the hillshade function in GIS programs? So I guess what I'm still not clear on, I would love to hear an explanation. If people in the Northern Hemisphere are used to the sun not being, you know, above us, whatever, towards the north, why do we have this, you know, as you showed in these experiments, why do we have this kind of inclination to perceive a light source from the north?
Yeah, I think I think it's not about the hemisphere you're born and raised in so much as more that being this right-handed, left-handed, I think. But the question maybe comes from this. I think maybe I didn't do a good job in explaining. So when you take the satellite images from the Northern Hemisphere and show it to people, whether they live in the North or in the Southern Hemisphere, they will see this effect the same way. The question is the moment the satellite captures the picture. So the satellite missions go around 10 a.m. to capture these. And if you think of the tilt of the Earth and the position of the sun and the satellite camera together in the same geometry, what happens is that in the Northern Hemisphere, then the light comes from the south. And in the Southern Hemisphere, at that time of the day, the light actually comes from north. So for this satellite imagery, the Northern and Southern distinction is really to do with the moment you take the picture. So it is less about where you grew up. So whether you grew up in the south or in the north, you would still see this effect like this. However, every time I show this slide, people ask me about this hemisphere question, whether that would be also different, because at the end of the day, we experience the sun a little bit differently. But I think that, so this we did also, this was my NACIS talk actually 2 weeks ago, but we collected data from South Africa and Australia. And we have collected one more data set from Switzerland to try to see effect of hemisphere versus handedness. And at the moment, I think handedness is stronger. Hemisphere effect is a little bit blurry. So we decided to collect some more data to see if there's really some, I mean, it's hard because this thing about Northern Hemisphere culture is dominant. Maps are north oriented, and it's not easy to separate this because you would have to find tribes that are not exposed to this Northern Hemisphere oriented cultures to be able to find this anthropologically, and it's hard. but we are still looking into it a little bit. So I don't know if it helps, but the findings are more about the location of the image rather than location of the people. Does that answer your question more or less? kind of, not exactly.
No, I think what I'm hearing you say is that people, yeah, like if you think about it more as an embodied experience of experiencing the sun, I guess I am just so used to like looking at images and figuring out where north is that I lost that for a moment, but I appreciate you bringing it back.
Great. I mean, the thing with the northern and so I think the natural experience is light is always above. I mean, it may be so it's not like the thing about the above left, that is not about the actual geometric configuration, because we are not stationary. We move ourselves. We move around. So it's not possible that we always experience the light from above left because of the natural configuration. But it is quite possible that throughout our lives, I mean, my desk light is on the left. I mean, I bet that everybody's desk lights are going to be on the left. So that kind of thing happens. I think this is maybe eventually becomes a statistic for your silent statistical machine.
Thank you for explaining that. I know that I had noted that, a long time ago. Why is it that the hillshade is coming from the northwest? But didn't really stop to think about it. So it's nice to know what that is. I had a comment about your 10 visualizations, which maybe it's an additional thing, or maybe it just falls into the category of metadata. But one of the things that we're very concerned about is accessibility, in particular for people who have visual disability. And just ways, I don't know if you've thought about ways in which maps in particular can be described and using text for people who cannot actually see the image, cannot actually visualize it, or visualize it with their eyes, but might be able to visualize it with their brain and a textual description.
Yeah, it's a super interesting area. I have not done any work on myself. I know one team in Czech Republic who's doing some project about it right now. So I was talking to her after listening to a PhD, early postdoc who presented on this. It's super interesting. I think that it's so for navigation. So it's for navigation. I think you can actually pretty much navigate based on sound. So when I'm driving, if I have a navigational aid, I rarely look at the map if the audio is on. So like turn left here and turn right here, and so there's that kind of effort. I think the audio is quite helpful. And then there's another industry-driven thing. I haven't seen it take off, but there was a vibration thing, like in the real world in the shoes. So you would have the navigation system, like if you need to turn left, your left shoe would vibrate a little bit. So like take a little left or something. I think they were like trying to communicate through tactile communication. And then there's, I mean, I don't think that was meant for particularly people who lost their sights, or people who can't see, but it was as an additional navigational thing when you're, I don't know, reading your phone or something. And but there's also the obviously tactile maps, like touchable maps, but this is very interesting with the cell phones. I mean, how do you get that sense from the digital devices? I think it's a sort of an unexplored area. Maybe sound is important, vibration is simulable. I don't know. So I'm speculating, but there are some groups who are working on it. I think Amy Loben in the US is quite interested in it. And one literature that I always find it super fascinating is like this brain research people that look at this spatial activity on blind people's brain scans. So there's a lot going on actually, which like the same places light up as the sighted people. So for me, this is like a sign that they can definitely build a map. But yeah, I didn't really study how to precisely do that. Anybody else in the audience? Maybe not in this room. Maybe I put that in the 10 QViz as a blog post, so Andy can contribute. So should I just go through the list still with the questions, or? Oh, we lost. So you're muted, I think.
I think Yelena also has a question on verbal knowledge. She mentioned that, could you talk a bit more about it? What is the definition of verbal knowledge and how it was measured?
Mm-hmm. Yeah, it is. So there are actually two things I remember from this literature. One is visual memory, and the other is the verbal memory. And also this study that I was showing you, how the mixed realism was better than the others. There we had, if you look at the visual tasks, the realistic, like if it was all photography based, realistic displays were competitive, and older people did nearly as good as the younger people, so their success rates were higher. So there's some literature that the visual memory is a bit spared. The verbal memory is also like that, which is not about processing speed of words. So if you think of language learning, I think that gets worse by age, I can tell from my own experiences. And maybe also like categorical place names or names of the artists or whatever, that can also go a little bit weaker. But memory, so experience-based verbal knowledge, meaning that you collect, it's like the wisdom thing, you collect this understanding of things over time, and when you need to express them or explain them, you actually do better than younger people. So this gets better with age. So this is something that I think we can all also anecdotally relate to. This is how much I can say about that.
Thank you.
My pleasure.
Any other questions?
So I don't know if you've considered this one, but how is it that we manage to abstract to a vertical view of a map, a bird's eye view? How is that something that we come to be familiar or understand?
Yeah,
being on the ground all the time, that is.
Yeah, that's interesting, right? We are not flying creatures. Why do we have two-dimensional maps, right? I don't know, there's a school of thought that says that actually our mind doesn't process the world in 3 dimensions at all, that it is in fact always kind of abstracted into these schematic representations. So the cognitive map, there's at least a school of thought that says the cognitive map is in 2D. It may be a simplification process. It may be that you don't retain information that is expensive to retain. So it may be a sort of a summarization process with, like go 100 meters and turn right, and then that's what you need to keep. You don't need to keep the rest of the 3-dimensional shapes and stuff at the same, I don't know. So there may be this kind of line of thinking. But I think the other might be the high places, right? So if you think of it historically, we to run away from the predators, one of the safest things to do was to climb a tree, or if you wanted to sort of observe enemy tribes attacking you, you would do, if Europe is full of these castles, every high hill has a castle. So it's like I think that we go to high places, and I think that might be giving us an oblique overview, which might be giving us the idea of drawing these sketches in 2-dimensional ways. Also, 3-dimensional drawing has been terrible. If you look at the medieval paintings, before people learned how to draw perspectives, we weren't very good at it. So it's 3-dimensional drawing is hard for us. So I feel like somehow the sketch was more intuitive altogether. But these are, again, a little bit like educated speculations, but I haven't studied this specific thing. What I studied is if people did well with this perspective switching. So if in this particular work I showed you also with the aging, we looked at this. We looked at, like, if you learned your route from a car first-person perspective, were you able to produce successfully a 2D map afterwards, sketch map? And the switch is interesting because it requires mental rotation. The other way around is also interesting. If you learn a route in 2D, how do you translate that into a real world 3D navigation? And in there we have also like some of the spatial tasks, what we considered predominantly spatial tasks. People were better at producing 2D sketches from those, but it was also harder with age, unfortunately, the perspective switch. Karen said something about the table lamp is on the right. Are you left-handed by any chance, Karen?
I'm left-handed, but if sorry, I was just plugging in the computer. But I'm left-handed. However, I also don't really work at my desk, so it's kind of a moot point. But
yeah, that makes sense. Joseph, left-handed too.
Oh.
Yeah, I mean, we should do a little questionnaire to see how dominant this table lamp thing is. But I think it's, yeah, intuitively, I think it may be more common actually to place it on the left. Not consciously, it's not, yeah, just like kind of intuitively. Okay, so there's a furniture design argument there. We are already getting some, and yeah.
Andy, I was going to say that, I mean, when I just moved, and when I organized my new office, you know, I went through every possible iteration of furniture in here, and I settled with the window and the lamp on my left, and I'm right-handed. Maybe I just really like that. Maybe it was because of the room. I don't know.
Yeah, it may be
Like
some sort of unconscious, yeah.
Where the door is, where the window is, you know, where you can put the big thing, you know, where the power outlets are, you know, where the closet is, all these things kind of forced
Right-handed, yeah.
to one place. And in order to easily turn on the lamp, it has to be closer to the door, and that means it's on the right. So I actually went and bought an extra lamp, overhead lamp. If I turn it off, then you can actually see that my previous desk lamp, and the daylight is coming from the, you know, from directly from my right. So I got tired of seeing half my face in shadow for, you know, till this fall, you know, for 6 months or whatever. I probably went and bought a new lamp that I can.
Yeah, no, that's good with the video. Lighting is important. My window is also on my left. I didn't even think about it until now, but yeah.
I've seen Yelena raise hand.
Yes, I just thought of another question. Thank you very much. It's such an interesting talk. It's so different from this kind of GIS traditional spatial analysis, analytically heavy work. So I was thinking, what kind of training did you have to go through beyond traditional geography? Did you take a lot of psychology classes, computer science classes, and do you still consider yourself mostly and primarily a geographer? And the second part to it is, what is your research community? Are you mostly still aligned with geographers and publish in geography journals? So is it more computer vision and psychology kind of things? I'm just really curious where you position yourself.
Thank you, Yelena. So it is, I mean, I've been sort of strongly embedded in geospatial communities for years. I go to International Cartographic Association meetings, so cartographers welcome this kind of research. Then I go to ISPRS. I don't know if there's the American version of it is ASPRS. It's the same sort of bunch, but global. I take actually also official roles in them. I run a working group on visualization, augmented virtual reality with the ISPRS. And in ICA, I'm a co-chair with the Visual Analytics Commission. And I also am in the International Society of Digital Earth. So there's another one that's kind of a Chinese initiative. And so I'm quite deeply embedded in geospatial people and world, and I go to these conferences. And I bring these as human factors research to these conferences. I push this agenda as much as I can. I'm not the only one. In cartography, there's quite a few others, but for the photogrammetry remote sensing, I'm kind of an oddity, but it actually seems to create interest. It's like when we organize sessions, it's packed. People come because they find it interesting. I mean, like you said, with these analytical engineering oriented talks, and then somebody says, okay, well, whatever you're doing it for people, and let's see how they receive this. So it does create some interest, and I imagine that might actually start a line of research also from there. Now, about the training, I'm actually basically an engineer. I studied civil engineering, specialized in geoinformatics, did my PhD in photogrammetry, and that was also very engineering oriented. But my interest in vision started by then. With the stereoscopic visualization, I started reading literature from vision science, which is a little bit neuroscience, a little bit psychology. So I've self-learned during that time. And then when I moved to University of Zurich, I started this eye tracking work in a geography department that was not an engineering department. And then my technical questions, I would put these ads for student projects, they wouldn't come. So I started switching a little bit more of the user experience questions. And there I also self-learned, there's a book that I give to every of my students. It's also something that I learned from doing psychology experiments. So it is a quantitative psychological methodology. So I don't see myself as a psychologist. I still feel like I'm doing psychology and also computer science HCI research, and I bring it, like always, kind of at the end of the day, I bring it to geospatial visualization. So I sort of still feel that I'm a part of this community more than the others. But I do go to other conferences. I mean, I go to sometimes eye movement conferences, and then there's psychologists, there's computer scientists, and then there's advertisers. And then there's me.
Great, thank you. Such a great intersection of all these different interests of yours, and you're very unique.
Yeah, thank you. I really like it. This this combination. It does stretch you a little bit, but I think it's a meaningful one, at least for me. And I'm glad to hear that it also resonates with you.
Yeah, thank you.
Can you talk as well more about the merits of working in this interdisciplinary way? I mean, you obviously just went through a gigantic presentation of all these wonderful things, but one of the things that I think is most useful and that you touched on in the presentation is that in a lot of ways, GIS is a set of skills that is like a suite, an analytic suite to be used in context. And so one of the things I look at a lot is how do I apply this outside, like to people that are not geographers. So I also have an econ background, and trying to explain to an economist, what's going on is sometimes a very, very interesting conversation. And so could you talk a little more about those intersections and how that plays out for you?
Of course, yeah. So it is also super relevant for me because I changed from geography to computer science a year and a half ago. And that's another kind of cultural shift, right? So, I mean, geography is extremely broad anyway. It covers, I don't know your geography departments, but the one that I was in had human geographers that were working sort of like migration and conflict, and it seems very sort of qualitative social science anthropology. And then you have physical geographers who are essentially environmental science geology background people, and then you have methodology. So it's like it's a huge domain. But then you go to computer science, and then you add medicine and astronomy and whatever you want on top of it, because it's like a sort of like you have a method and you can apply this to any domain that you kind of feel comfortable or find a collaborator in. So it has become an interesting question also from that perspective for me. It's like this, how far can you go with this interdisciplinarity? So it can be you can stretch yourself too thin, and then your knowledge might become kind of naive. So you have to be a bit watchful not to do that. So if you are trained in one domain and you are trying to do something that is related to other people's expertise, I think it's very healthy to find collaborators from those domains and make sure that you sound the stuff with them. And it's super educational if you can do that, if you can actually go to conferences where, let's say, psychologists and geographers can come together, which happens with spatial cognition, for example. So there's certain ways to try to ensure that you're not and it's healthy to ensure that you're not too naive in what you're trying to do. And if I review for computer science journals, I see the opposite too. Like they sometimes reinvent cartography, like something that has been done by cartographers in 60s now are heated as a new computer science topic. This kind of thing happens because people don't read each other's domains. So I try to watch for that. So it can become a disadvantage if you do it this way, but it can be also an advantage if you can somehow find the good way to work with these, when you identify when you are not really strong in something and find someone who is, and then compensate or complete this gap, or acknowledge where your weaknesses are. And I think that already requires some insight, right? So people usually don't, they don't know what they don't know. So this is already a difficult thing to compensate. So I did sometimes find it difficult in my scientific identity as I grew up, where because it's you need to be associated with a certain expertise, and if you don't, then people have difficulty knowing what you're doing, and it can become a little bit of a threat. But I think that eventually, if you frame it the way that I did, for example, everything I do, I eventually bring it home to visualization. So I look at computer science, I look at psychology, I try to understand vision, I try to understand attention, but all of it I'm actually bringing back home to where I'm most trained in. So this is probably a good way to go about it. I don't know if this is the direction you wanted to hear about, but eventually it worked for me. I mean, my grant applications have been successful. So that way, I think, is a good indicator that this bringing knowledge from another domain and making sense to people in your own domain is actually not bad.
No, that was super helpful. I think that definitely, balancing off, and certainly a lot of really helpful tips, especially with, creating teams that are interdisciplinary in a way that you can grow strength together. Yeah, no, definitely good warnings throughout. Thank you.
Yeah, thank you. And some of you who have to,
Yeah, thank you so much, Arzu. Really, I really appreciate it, and it was a pleasure for me to listen to you one more time, and I took lots of notes, and probably I will email you later because I don't want to keep you late. It must have been midnight now.
It is what I have said, but it's okay. I'm a night owl. If you asked me to get up at 4 a.m., I wouldn't do it, but staying up until 4, no problem. Thank you very much.
Thank you. Yeah, we have a happy Mappy hour, and I think Becky shared the link. So the ones who would like to join, please join us for the Mappy hour. And once again, thank you for your speech. We really
thank you everybody for attending and enjoyed the Mappy hour. Happy GIS Day. And thank you very much, Seda.
Thank you.
Thank you so much, Arzu. That was really incredible. Thank you.
Thank you very much.